Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome my colleague and friend Rita FIORESI from, did I pronounce it correctly? Was it correct?
Excuse me? From?
Did I say your name correctly?
Perfect.
Grazie mille. She is from Bologna. She was supposed to come here in person, but because of an accident with her hand, she couldn't. But we are very happy that she still agreed to give her talk online via Zoom. And it is about a topic which is very dear to my heart because it's about reduction of quantum principal bundles. With my colleagues, we did it more in the setting of sister algebras. I mean, it was just scope algebras, but for us, we view them as dense subalgebras of sister algebras. Whereas what Chiara does, she has this approach which is based on algebraic geometry. So it's like kind of orthogonal to what we do, and this is why it's interesting for us to see an alternative theory for reductions of quantum principal bundles. Rita, without any further ado, the Zoom is yours, the floor is yours, take it away.
All right, so first of all, thanks so much to Ludwig and Piotr for this invitation. And as I said, I really feel a lot of regret for not being there. And being my fourth accident in less than 12 months, 3 of which to my right hand, I must start being a little more careful to what I do in my life. All right, so this said, let's go to the question of reduction of quantum principal bundles. And somehow, Piotr, I don't fully agree with your assessment that I'm orthogonal, because I strongly believe that the theories is indeed the same and can be viewed from different point of view, but the definition, as you will see, it's really very compatible with the one that you give in your paper, and I will also comment on that. So.
I'm very happy to concur with you. So let me reformulate what I wanted to say. So we are not orthogonal, but we have different scalar products.
Oh, all right, let's see. Okay, so before I start the mathematics, let me take just 2 minutes to advertise the Callista cost action that you see the logo right here. It contains 5 working groups. And as you can see, there is a working group called Noncommutative Geometry and Quantum Homogeneous Spaces. And I really strongly invite you all to participate if you're not already participating, because if you do, of course, we welcome you. That is the first thing. And the second thing is that we can pay for your, short-term missions, for your dissemination conferences. And you just go ahead in this cost website. It is very simple. It will take 5 minutes. First, you join the COST Association, Cooperation in Science and Technology. And then secondly, you join the Cost Action Callista, which is 21109. And then you can, basically get our money. And we'll be so happy to give you this money. So this is the...
Wow, I wish it would happen more frequently. Somebody just gives you money and is happy to do it.
No, come on. I mean, this is money was given for these working groups. And one of them is really called, quantum groups. So, I mean, we are in the right community to apply for this money. Of course, you have to be affiliated to European institution. But apart from this, you can participate. Now, these are the type of events that we fund. For example, training schools, workshops, and, just general meetings. And I write, propose your event because what I'm trying to say is that for the 25, we are full. But 2026, we still have to decide. So if you want to propose an event, why not? I mean, this is, okay. So this, I promised 2 minutes, it was 3 minutes, but finished with the cost. And I will share these slides afterwards, so you can find the website and you can join. Now we go. Yes.
We organize an annual workshop for students in Bendlevo, in the Banach Center. Would it be possible to do it with your funding?
Why not? Yes, that is perfect. let's discuss it at a later moment, but why not? This money is especially for young people. We prioritize young people, and we can either directly fund your meeting, or even better, we can fund the young students to participate to your meeting, okay? So
what we like to do, because all that we have, we cannot support any students. We just have some support from the Banach Center.
but that's perfect. Yes,
all that you need to spend is 200 euros per week. That's all. That's the whole thing.
yes,
So-
but so let me tell you this. It's very important. I'm glad you asked this, because now there is an opening, and if Paolo is among the audience, which I cannot see, he can say that there is. Paolo, are you there? Paolo perhaps is not there. Okay, but there is an opening now, 1 month, the month of October, where you can apply. If you don't apply within November 3rd, then you cannot apply for 6 months. So go to our website, apply for the money, ask the students participating to ask for money, okay? Because it is the moment.
Okay, thank you. Let's do math.
All right, let's do math. So what is the plan of my talk? So I want to talk about principal bundles. I am very aware that all of us know what they are, but it's very important for me to express them in such a way that the quantization will come easier. Then I will give the definition of quantum principal bundle, and I'm aware that my definition is slightly different from the one present in the literature. I will explain. And then the reduction in the classical setting and the reduction in the quantum setting. And this, the most important section for me are the examples, because you can talk a lot, but the thing is that you need to have meaningful examples. And this is a joint work. Everything I'm saying is a reduction on quantum principal bundles over non-affine basis. That was, as you can see, it is 2024 work, joint with Emanuele Latini and Chiara Pagani. So this is the plan. Okay, principal bundles. So let me give you the definition. So we have that a principal bundle, if you consider E and M just for the moment to be topological spaces, very simple. So you want a surjective continuous map of topological spaces. And then you have a group P. I'm sorry, I call it P because for me it's a parabolic. So for me, the application that I see is when you have a special bundle, but I will say it, we'll say it in a while. So P is a group for me, and it will act freely from the right on the topological space E, which is the total space of your bundle. And then you want it to act transitively, freely and first freely and then transitively on the fiber. So if you give me a point of the base manifold M, essentially P minus 1 M is a copy of your group P. And then I write under parentheses, you want E to be locally trivial over M. What do I mean by this? You want that E locally looks like M times P, okay? The base times the group, locally. This is the fourth condition, is a bit restrictive. We will see later on whether we really want to impose it or not. The truth is that in all our examples, both classical that we're interested in, both classicals and quantum, we do not have, we do have this condition, but in general, you may not have it. Clearly,
now,
yes.
If you allow me to comment, because there are many.
Yes, of course.
If you look at the original definition of a principal bundle, which is due to Henri Cartan, the local triviality was not there, right? And you can very easily construct nice natural principal bundles which are not locally trivial. It just that here what you have to do, and this is why people grow so fond and used to local trivial principal bundles, that whenever your structure group is a Lie group, and that's what you typically have in differential geometry, theorems that guarantee you local triviality. It's not an assumption. In particular, if you take an affine group, you must have local triviality. It's not an assumption. It follows. You can prove it. Okay.
No, I put it under parentheses because I am aware that it does not belong to the definition. Yes.
Aware. I'm just trying to mention it to students that
Sure.
and this original Cartan definition of a principal bundle without local triviality is very easily translatable into Hopf-Galois theory.
Of course, of course.
Geometry is inherently global. So being able to do things globally is easier than to do it locally. And at least in the realm of sister algebras, okay? At least in the realm of sister algebras, going to local triviality, not piecewise triviality, local triviality. So really trivial open sets, not closed sets, okay? Because sister algebras describe closed sets, not open sets. It was a very hard problem, which was solved only recently. Okay, so local triviality for compact quantum principal bundles given in terms of sister algebras, that's a very hard notion.
Okay, this I must confess I don't know because we are very far from the compact setting as you will presently see. So
Sure.
in this example, okay.
That's something, Thomas, say.
Okay.
Good question. If you forget about local triviality,
yes,
then of course you are assuming that your P is somehow kind of compact group, or maybe because it was a parabolic group.
Okay, I understand what you're saying, but for the moment it's very general, okay? So you have to bear with me just a little bit, okay?
You can produce pathological examples with this.
Yes, of course.
Which can you avoid assuming properness of the action?
Yes, I am aware that this is a very general definition, but very soon we'll be immediately going to a more restrictive condition so that your correct remark will not apply, okay?
Okay, thank you.
Okay, I'm sorry. And of course, this definition that I gave for, topological space, that's not really what we're interested in, because you may be interested in a C infinity category, for example, or as myself, you'll be interested in the algebraic category. And this is the category where I'm more comfortable with, and this is the category I really want to study. More precisely for me, E is a algebraic variety over C, an algebraic, so very, what can I say, mild situation for the moment. And then you look at a bundle where P is an algebraic group acting on it. So it's a very particular condition. Now, the situation, yes?
I think Tomek made a very good point. This definition, I mean, you must have properness of the action to call it a principal bundle. That's not negotiable.
Okay.
And of course, it's automatic when P is compact. But it's very important that you see, if you have local triviality, then freeness is basically automatic because group acts free out, and if you are free at every local piece, then you are free everywhere.
Sure.
But properness is a global condition, even classically, is a global condition. So you can very easily construct an example of a locally trivial, if you want, bundle with a free action, but the action will still not be proper.
Okay.
It's not a principal bundle.
Okay, I see.
Okay, so you definitely should assume that P acts freely and properly on the right on E.
Okay. I'm not sure about this, but I'm having a very particular setup, and perhaps.
No. But that's if you really want to have it, call it a principal bundle, the action must be proper, and it is not implied by local triviality.
Yeah, but properness in the algebraic category not so straightforward. But okay, let me tell you the example I wanted to. Is a prototype of example. So, are you happy to consider SL2C going onto its quotient by a parabolic subgroup? Would you call this a principal bundle? Is a question for you, Piotr. Okay, then this is really the prototype of what we're looking at. So we're looking at yes.
Yeah, actually, proper, no problem. So
okay. I thought properness was linked with some compactness, but okay, whatever.
I mean, compactness implies properness. It's like
Yes.
the trivial, yeah, but not the other way around. Yes.
Yes, but the algebraic category is a bit awkward with that. But okay, let's go.
One of the thumb is that if your action is free and proper, then the quotient is Hausdorff. You see, and your
problem. That's a problem because we're not looking at Hausdorff quotients. That's why I was warning about that. See,
Hausdorff.
no, it's
okay. Okay.
okay. I will. You have to allow me. Okay, you have to allow me because there is a bit. There is a bit of complication here. But so this is the prototype. As you can see here, we are looking at local trivialities. So we have the P is parabolic. Okay, and then you have that if you take an open of SL2C where you take A is different from 0, you have 1U01. Decomposing TP0T minus 1. So you have this decomposition. And this shows you that your open set decomposes as, an open on the base, which is the projective space. So it is covered by two affine. So U is an affine coordinate. And then the parabolic, TP0T minus 1. Similarly, if you take C different from 0, then you find another open set, V minus 1, 1, 0, which is giving you coordinates on another open set of the projective complex line, and then times the parabolic. So this shows you a cover of SL2C of two open sets, and this project into P1, and this is clearly giving you the local triviality. So we are happy with this picture, are we?
Yeah.
Yes. So I give you a little bit anticipation of the future is that I will be interested in the topology that is generated by these two open sets. So I will have a topology that you see where you cannot really separate points because you have only three open sets, U1, U2, and the intersection. So it's a bit strange in some sense, right? So, okay. I don't know if you did. Okay. Okay, so let us go with the definition of Flaum that appeared in communications in mathematical physics in the 80s or 90s, I forget. So we say that, sure. In the 90s, okay. I should have been precise. I have all the references at the end of my talk and I should have put the dates. So we have that P from E to M is a P principal bundle. So I write an if and only if because this is the definition of Flaum, but then you have to show it is actually compatible with what you had before. So you need a sheaf of H comodular algebras. So H is the coordinate algebra, so it's the algebra of functions over P. You want to consider algebraic, you want to consider differentiable, even continuous. It depends on the category you're interested. As I say, my category of choice is algebraic over the complex field. So we want that there is an open cover of the base M of the bundle, so that if you look at the co-invariant on this cover, where you take the pre-image, I'm sorry, I wrote pi here, it should be a P here, this is a mistake. So if you look at the pre-image of the cover, you want the co-invariance of H, is an of algebra, of course, must be isomorphic to the functions on the base. And then you also want the trivialization on this open. So in the moment you are asking that you want f of ui isomorphic as left FUI co-invariant modules and right H comodules for all I to that tensor product, you essentially are asking the local triviality, okay? So this is... Yes.
Let me jump in, Rita. That's very important to emphasize that when you write this isomorphism, this is not an isomorphism of algebras.
Exactly, not necessarily.
Not necessarily. You see, this was this wonderful big discovery of Flaum. that these are in general smash products.
I see.
Or if
Very good.
trivial coscycle cross products, okay? And it is necessary if you want to do anything non-trivial, you have to do it, because previous attempts by Kondratsky, Budzinski, which were a little bit earlier, they insisted on having tensor product here. But this kills examples. I mean, it's just a wrong assumption. One should really bear in mind that the trivial principal bundle is not the tensor product. It's the smash product.
No,
okay?
no, I don't want to expose and say it is wrong, except that you have less examples. You have less in the quantum setting. If you insist on having isomorphism of algebra, you are with less examples, of course. I mean,
it's an inadequate definition, and also it's much you see, because it's very easy to reformulate it in the following way. Even in the classical topology,
sure.
if you want bundle is trivial, what do? You take a G equivalent continuous map from your total space to your structure group, and this is much.
Piotr, you are anticipating my talk, so you are not allowing me to. I will have it later. So later on, we'll think, okay, about this characterization and how this is so important for the construction. Indeed.
I just wanted to emphasize that what you wrote here is very important and very correct. That this is only as modules and right-age modules, but not in general as algebras.
Yes. Now, what I wanted to say, which is perhaps less obvious, is that if you have an open covering, because I think Flaum was not adequately understood at the moment, but if you have an open cover and you tell me what happens on an open cover, you are actually telling me the whole geometry of your bundle. Why? Because if your bundle is not, what can I say, an algebraic variety, so if your bundle is not captured by a ring itself, if you have a cover by affine open sets, and if you tell me what are the rings on each affine, you essentially are recovering the whole geometry, because you are recovering, you know, by patching what happens on the whole bundle. I don't know if you understand. I will give examples, but it's very important, this point. The sheaf is capturing what you cannot capture when you don't have an affine object, when you don't have an algebraic variety. We will see it in a moment as examples. Okay, so I really, this was very influential, to at least to me, this Flaum. I perhaps not so known. Okay, so now let us look as an example of a classical principal bundle, because we want to go to reduction, so we have to understand this first. And then we look more in detail to the example I was giving before, which is SL2C projecting on the base P1C, where P is TP0T minus 1. Or if you prefer, I use two notation here because I also want to, you see my cursor, right? You see what I am highlighting? Yes, great. Because if you take the quotient of the coordinate algebra of SL2, which is this one, it is generated by ABCD modulo the determinant relation. Now, if you take the quotient by C, essentially you are destroying the determinant relation, so you can get rid of D, and you have AB, A minus 1, which I call TP, T minus 1, just to stress they are different. Then you can define a sheaf by specifying what are the rings on the open sets U1 and U2, where you say, well, I can invert just the element here, the A11 element, or I can invert the A21 element, and then you can build a sheaf. You have to tell me what is the ring on U1, what is the ring on U2, and then you have to ring the intersection, U1 intersect U2, which is when you can invert both. This defines a ring, okay? The problem is that defines a sheaf. The problem is you don't need more open sets, because if you know what happens on these open sets, you know the geometry of this object. I know this is a phrase which is very intuitive. It's not mathematical, but I swear I'm writing another paper with somebody else that is exactly making this phrase rigorous, showing an equivalence of categories between open covers of schemes and schemes. Okay, we're trying to do this thing in a very, very general way. For now, I think my talk will be just brief. Okay. I don't know if these slides make sense to you guys. So you can view this.
I mean,
Yes.
they don't look disturbed.
What? They don't look disturbed. Okay, this is enough. So essentially, here you see the problem is that SL2C is a perfectly good object, is an affine variety. So you coordinate algebra, you do have it, right? But P1, you don't, because P1C is this projective object that doesn't have a ring associated to it. You can associate a graded ring to it, not a ring. And then you think, oh, well, Rita, you know what? It's okay. You associate graded. But then I will show you another example where you don't even have that. So you have an object that is not an affine algebraic variety, is not a projective algebraic variety. So what do? You need the sheaf. I'm trying to convince you that you have to go beyond the rings. You have to look at sheaves of rings, of course, not necessarily commutative. But I'm not alone with this. I forgot to put the reference, but there is Van Oysted, there is Rosenberg, Skoda that wrote things about this, and clearly I'm not the first one suggesting. Okay, so I mean, I must give credit to all these people and more. Okay, now it is important to understand the local triviality for the open sets U1 and U2. In this case, we have it, and it happens that this is really a trivial extension in the sense that it is cleft. Okay, so we will speak about cleft later on, but geometrically, you have that U1 is indeed U1 bar times P. So your point.
Left is not necessarily trivial. You
But
can have a non-trivial one is cleft. So
very
say
true.
cleft, not
You are right.
the same.
Thank you for catching me when I'm not precise. Here it is cleft and it is also trivial. This is a baby example that is very, very simple. Okay, so this is really everything you can imagine. Of course, if you go to more complicated example, life is not as good as this case. But so in this case, you really have a isomorphism of algebras. And by the way, here we are in the commutative, so it's really like no problem at all. We have the CSL2, where you invert the element A, can be made totally isomorphic to the tensor product of these two rings. That, by the way, it is the ring of algebraic functions on U1 times P. Okay, so it is really simple to check this exercise. And you can do the same calculation also for U2. It's a bit like there is no difficulty. And everything works really nice because locally you have that the functions on the base are recovered as the covariance with respect to H, the parabolic subgroup. Okay, so this is a baby and a simple example. So far, so good. We are happy, sort of.
But if you somehow make sure that you are.
Yeah.
Yes.
So for sheaf, like you have to assign every open set to a module, right? So it's a.
I am sorry, I cannot hear. Can you rephrase?
To have a sheaf, we have to assign every open set to.
Very good, very good, very good. You are saying correcting, yes. But I am interested in a very stupid topology. The topology that has U1 and U2 as open set and their intersection. This is a perfect topology, okay?
Okay.
Now, it is a very good question saying, oh, but Rita, you're doing something that is not the usual thing. yes, this is not the usual thing, but in my paper that I promise it will be ready by the end of 2024, we prove...
Remember that you are recorded, so you might be held accountable to your promise.
Yes, yes, because my co-authors are working as we speak. They should be working on fixing the details. We prove an equivalence of categories where you give me a cover of your object and you give me a sheaf on this cover, and this is totally equivalent to give me a sheaf on a much bigger cover. What is the trick of this? The trick is that when you give me the ring on an affine set, you are essentially giving me the sheaf on that affine set. That's exactly the trick. Now, it seems to you that what I'm telling you is trivial, but if you want to do it categorically, really, there are fine details that are not so obvious. So this is why it's taking us a long time. Thomas has a question.
Yes, I have a comment. That,
Yes.
You started from some advertisement about sheaves, but in this
Yes.
situation, if you fix a covering,
Yes.
you are actually talking about co-simplicial algebra.
But here we are with experts. Of course, we are talking about simplices. In my new paper, we will associate a simplex to this. You guys know too much. I should have done a talk at much bigger level. I wanted to make it very accessible. You are very correct. Yes, yes.
Okay, thank you.
Yes, indeed, indeed. You'll be one, hopefully, reading our paper, because right now we're not so sure who will have that has non-commutative geometry, sheaves, and simplices, semi-simplicial sets even. So it's going to be that. You are correct. Yes, yes. But this, moreover, there is also the idea of co-sheaf hidden here. But okay, let's not talk about something else. Okay, so I'm glad of the interest. Now we go to quantum principal bundle, and the notion that we gave was reworked in such a way that is ready. Okay, we need to make a very quick disclaimer. I know we all know this, but let's fix the notation. So when we say H, we always mean an off algebra. No, all of our off algebras will have bijective antipode by hypothesis. Assume that any algebra we take is unital, so and is over a field. So we're very, what can I say? We're in a very happy situation. And then we say the notion of principal. Okay, so we look at the H comodular algebra. So there is a coaction of H on an algebra. This coaction is principal if when you look at the co-invariants, you want it to be a off-Galois tension. So we want the canonical map to be bijective. And I even write it so that we all know what we're talking about. And I even write the co-invariants. And then we want somehow what can I say, this faithfully flat condition, because this is a technical condition that makes life much easier. And actually, it is proven that, for example, the Reshettikin, Faddeev, Tatagian algebras have this condition. So it's like there are many, many examples of this. Now,
Rita, if you don't mind me saying so, faithfulness is not just a technicality, it's fundamentally important, because this is actually a tantamount, it's equivalent to the equivalent projectivity. It is equivalent to the existence of a strong connection. It's equivalent to having associated, but you can, really do non-commutative geometry with this. So that's not just a technical. And if you look into the history of Galois theory, then you discover that first definitions actually assumed that these Hopf-Galois extensions were faithfully flat. So it was weaved to the definition from the very beginning, and I'm very happy that you use this term principle, because that's exactly how we called it when we wrote about these piecewise trivial principal comodular algebras.
Yes, so I didn't want to say it's not important, because faithful flatness, it's very important. And actually, it is like a cornerstone of the theory of descent, without which you can't do anything, right? I mean, this is like However, it's a condition that it's very, how can I say, as you correctly say, it is equivalent to many things, and it's not really the easiest thing to get around. And for this reason, I didn't want to dwell into this, but thank you for making it even clearer. So it's...
Some of the best and the most spectacular theorems of Schneider are done exactly for faithfully flat case.
I am aware.
Yeah.
Schneider and Takeuchi, you know, they did a lot for this theory. Now, we say that Off-Galois extension is cleft if there exists a convolution invertible H comodule map, which is called a cleaving map. And as somebody said before, you know, this is equivalent to say that your algebra is the smash product of, you know, the coinvariants and H.
No, that's not true. This is not a smash product. It's a cycle cross product.
No, I am so sorry. Yeah, of course, the cocycle cross product. Yes. The cocycle is coming to the cleaving map. Yes. And however, when you have this, yes. However, you have even a stronger condition when you have the isomorphic as algebra of the tensor product. This is even like a stronger condition that you can.
Isomorphism with a tensor algebra is just a wrong condition in the non-conjunctive setting. If you just make the cleaving map an algebra homomorphism, which renders it automatically
correct. Yeah, I mean, I don't know what to say. I mean, it can be called a trivial extension if you prefer. So it's the trivial case. You can say that. Yes.
Yeah.
And of course, if it is, I mean, it's not of course, but you can prove that if it is cleft, it is also principal. Okay, so this is
that's immediate.
Almost.
That's immediate.
Yeah. Now let us look at the quantum principal bundle. So now I know that we're going to have, like when I say disagreement on terminology, so forgive me. So we say that we have a quantum ring, the space, this is due to Manin. If you have a classical topological space, so you have a topological space in the usual sense, and then we have a sheaf over M of non-commutative algebras. This is common. Artin worked on this, Michael and other people. And then we give this definition that was back in 2021, where we say that we call it H quantum principal bundle over a certain quantum ring, the space, a sheaf of H comodule algebras, and then we have an open covering that we don't require it to be finite, but actually in all our example, it's finite, so that the coinvariants on this cover are exactly, hey guys, are you boycotting my talk?
Me.
Okay.
Whoever doesn't, please remove this.
Very funny. Okay. So, and you want on this open cover only because, you know, when you're quantizing, you cannot really ask for all open, that the coinvariants of your sheaf are really the functions on the base. For me, they're always algebraic functions in my examples. And then you want UI to be a principal H comodule algebra. We also have a little variation of this, where we don't ask it just on an open covering, but on a base for the open. Because when you have a finite cover and you look at the topology generated by this cover, then this topology is going to have as base the finite intersection of these open sets. So it is a very small, and as correctly Thomas was saying before, this is actually a simplicial structure, if you think about it, even graph structure, but more precisely simplicial, because then you look at, you know, you can get away with graph because you look at the open sets as nodes, and then the intersection of two open sets as edges. But then if you want to look at three intersections, they become like faces and so on. So there is a hidden simplex. I'm not sure if you were thinking about that or something else, but this is the structure that I'm looking in the other paper. Okay. So this F is called the locally cleft if it is locally cleft, and locally trivial So if your extension is clef and is called locally trivial, I didn't write it, but if it is really isomorphic as an algebra, I know Piotr, you don't like it, but this is also possible. Now we realize that this definition goes into, how can I say, in conflict with other definitions present in the literature, where you want also the Atiyah sequence condition. So you want the function on the base, you know, to have a certain exact sequence, but we decided not to go into that because especially this Atiyah sequence comes when you're looking at the differential calculi, so it is in other contexts. We felt that we could be a little more general. Now, I don't dare to say if there are questions because perhaps the people that ask the Atiyah sequence now are killing me because I don't ask it. Piotr, you were more modest because you say principal algebra, so is better, but we decided to say this. I don't know. Are questions about these comments?
No, I have only one trivial comment, if you don't mind me saying so.
Not at all, yes.
It's not my fault. It's Thomas Maastricht who is guilty. And it all happened in Rome. We just couldn't communicate with each other because you see, in mathematics, if you just open Wikipedia, coinvariants mean a quotient construction. We are not doing coinvariants. We are doing coaction invariants.
Yes.
And so that's Hopf algebra people hijacked the wrong term from general mathematics terminology. So after that conversation with Tomek at the Rome airport, I'm now very religious about it, but I never call it coinvariant. I call it coaction invariance. But
I see. Okay, so I apologize, but I'm not the only one using this terminology. So I'm.
He didn't understand what I meant because coinvariants have a meaning in mathematics, completely different to the meaning given it here.
Okay, coaction invariant makes you happier.
Yeah, that's perfect.
I try to remember that. I promise. All right. No further comments?
No, we can. Wow, we have enough. Yeah, we can go on.
Okay. Now, I wanted to convince you that everything that I did in my calculations for the classical setting are immediately generalized to the quantum setting. So I take the very baby example of the Manning relations, giving me the quantum special linear group that I guess everyone knows. And then we look at the open cover as above. So we obtain a quantum ring in the space just by looking at the two section, two affine rings. And of course, you should also check compatibility condition on sheaves, which I don't have the time to study. But the most important thing is that you can build a quantum on the quantum ring space, a quantum principal bundle, which is exactly same as before. So you take U1, U2, sorry, this should be a U2, this one escaped. So and it's very annoying, there should be a C here, whatever. So is a cut and paste gone bad. So
Yes.
FU1, FU2, and F of the intersection. And you obtain a sheaf of H comodular algebras for this parabolic on P1C. And everything works really nice. And in our paper with Aschieri and Latini, we push this theory beyond this because not only we look at G over G mod P for SL2, but we take any algebraic group, a quantization of this algebraic group, a quantization of the parabolic, and then we construct a quantum sheaf, quantum principal bundle over the flag G mod P. This is our construction in that paper, but I'm not going to go over it because today I will speak about reduction. Yes, Thomas, please.
Are you assuming in the general situation the ORE condition?
Yes, indeed. So I'm very happy that you are asking this. In that paper that I'm not going to describe, you are indeed, you have to assume that all your localizations are OR, not only this, because in this case you can check by hands, so it is very simple. But in the general setting, when you're taking an algebraic group and then you are inverting this to get U1, U2, UN, right? You are inverting all of this. First, you have to ask the OR condition for each of the elements. But then you have to ask more. You have to ask that it doesn't matter the order in which you perform these OR localizations. So the ring that you get is independent from the order of the OR. And I had a very long discussion with Skode about this, that he tells me in the last talk I was able to hear, he tells me that actually there is a better way to say this, and perhaps there is, but in our paper we wrote it in that way. Okay, so I don't know, Thomas, if I answered to your question.
Yes, thank you.
Yeah, it is in that paper. Okay, so everything goes well. So let me go finally to the main, the meat of this talk, which is the reduction of principal and quantum principal bundles. So the first thing I describe what is the reduction in the classical setting, then I'll go in the shift theoretic point of view. And of course, I have like an affine and a non-affine picture, okay? Okay, so now I know, Piotr, you want to say this thing about the section, but you have to bear with me. Section will come later, okay? So it's general definition. So suppose you have a principal P bundle and you look at the subgroup. Now you have another principal K bundle. Now we say we have a reduction if we have a K covariant homeomorphism, because we are very general here, just the continuous. So that you can somehow embed, in some sense, E0 into E. Okay, so it is somehow a sub-bundle. This is a very strong condition. Some people ask it is closed. Fine, it will be closed in most cases. But reductions are difficult. They may not exist, while something called prolongation always exists. So I will not get into prolongation, but now I'm looking at my prototypical example again, where I look at the reduction where instead of going straight to the, so from SL2 you can go to the P1C, the projective line, but you can obtain like the bundle P0, where you go from SL2 mod N, the unipotent group, and if you quotient by the torus, you still get the projective line. And it is not a difficult, it's a simple exercise that you have a reduction. Now, having a reduction, for the case of SL2C mod N to SL2, you need a map going, the map phi, right? You need it. In general, for parabolic geometries, where you have P a parabolic and N the unipotent radical of that parabolic, you still have a section. So what I'm trying to tell you is that if you take an algebraic group, and if you look at the parabolic, and you look at unipotent radical, you always have a reduction. This is, to me, I don't want to say surprising, but it's not obvious, this fact. And you need to prove the existence of this section. Can we do it in the quantum? For the moment, we cannot, because we can do it only in a special case. I will show you the special case where we can do it, the extension of this. But we believe that can be done. Okay, we believe we can do the theory, except that, Chiara sadly abandoned us and she's gone to work with Francesco. But if she were in Bologna, we would have pursued this road and produced the reduction for quantum parabolic geometries. That was the idea. But what we're going to show to you now is like a special situation which we think is interesting. So far, so good for the definition. Are we happy?
I just want to make a trivial comment in case you didn't notice it. If you take your K to be the trivial group, then the existence of such a reduction is equivalent to triviality of a bundle.
I see. Yeah.
Yeah,
okay.
That's why you see that there is an obstruction, right? It means that the reductions might not exist.
Absolutely.
because in particular, not every principal bundle is trivializable.
Yes. And yes, so I'm making a comment here about, you know, all these diagrams. They're a bit of a headache, but you see you have SL2 going to SL2 mod N. So in one case, the fiber is P. In the other case, the fiber is the torus, which we call K. And as you can see, the fact that you can go the other way is not obvious at all. Now, for the case of the unipotent, you can easily show that SL2C mod the unipotent N is a C2 minus the origin, okay? This is not an algebraic variety. It's certainly not an affine variety, but it's not even a projective variety. This is a very badly behaved object, despite the fact it's an orbit, right? So it's nice because that's the orbit of E1 under the action of SL2C. Despite the fact it's an orbit, it's not a variety, but this is known, is open in its closure, it's well known. And the only way to really deal with it, it's with a sheaf. So you have to look at it as a scheme. There is no way out of that. So if you want to see the reduction, you have no choice because your reduction is not an algebraic variety, not affine, not projective, and the base is a projective object. So you may as well go to the generality I suggest. Wait, Thomas, let me finish, then I answer. In order to show that you really have E0 to E, I produced an embedding, and you can show it is gluing and is really giving you what you want. So it is really true. But if you go in the book by Chap and Slovak, they wrote a book about parabolic geometries, they will give you the whole thing. I mean, they give you the whole theory where they show you can always find this. So essentially what I'm trying to say is that the sheaf theoretic approach is not for the fun of it, which would be fun, of course, but is necessary to quantize these objects. Thomas, what is the question?
The question is about topology.
Yes.
Of this quasi-projective
Yes.
variety. Are you assume? Do you assume that that this is also finite?
Yes.
With a distinguished. Okay, so we have a distinguished covering for this quasi-projective.
Yes, yes, but you are very right, saying, you know what, your construction depends on the cover. I will try to convince you, unfortunately, without the paper that rightly Piotr is holding me accountable for, that it's really capturing and the geometry, not only this, but there is an equivalence of categories. So if you give me a sheaf, you're giving me a family of such covers, it doesn't matter which one you pick, you still get the same object. And so there is, it is very funny. It's one of these things that kind of obvious, but if you want to write them carefully, it's a nightmare. This is a nightmare we are in. Okay. Yes, but we'll take
what is your compatibility condition for these two covers?
But this is the other paper, Thomas, really. There is something called, let me tell you just a hint because I see you are curious. So there is something called the localization of categories. So you want to tell when two covers are isomorphic, so to speak. And then, but then they don't match, right? So you need to be careful. And this is where localization of categories came. I was speaking with Barbara Fantecchi. That's where we got the idea. But Barbara is in CISA, right? Is in Trieste. Where is she? So you can ask her because she knows about that. We're talking about it.
Barbara Fantecchi.
Huh?
Barbara Fantecchi.
Barbara Fantecchi, indeed. She's there. So, but this is, I'm sorry, Thomas, this is taking a bit far from where I want to go. I'm sorry about that. I want to keep going.
Okay, thank you.
Okay, now let's look at the reduction of quantum principal bundles, so not principal bundles. So I put down the definition. This was due to Gunther, but then I read it in a paper by Ayatz, and for me, it was, I don't know, it was, since you, Piotr, applied it to something, it looked to me clearer than Gunther, because Gunther is a very theoretical paper. You read it, right? While in the paper by Ayatz is a bit more concrete, to me at least. It also depends on the person reading it. So we're looking at the, yes, Piotr.
Well, let me, since you are getting historical, I say historical, not hysterical.
Yes, yes.
Let me just say that there was also Schauenburg involved. So
yes, yes, indeed, yes.
What happened was that Ginter was a PhD student of Schneider. And
This
did much of the job, and he was looking at pointed algebras, if I remember correctly. But then I think Schauenburg generalized it to arbitrary algebras, and this is when I was in Munich. And what they explained to me is that you had this reduction theory, but they were missing the last step. They're missing the step in which you don't only have somehow the equivalence between, you know, reducing ideals and these appropriate equivalent and maps, but they had a bijection between equivalence classes. So somehow they had the homeomorphism of base spaces, okay, whereas we proved that we have actually an equivalent homeomorphism of principal spaces. So that's just an analogy, okay? I'm not talking really bundles. And the last step which we did with Rainer Mattes, and that's I was in Munich, and it was very natural for me to dig into it. And I must say that this is Hopf-Galois theory, in my opinion, at its best, because you see all these absolutely incredible subtleties that pop out. All this, my goodness, how is this action is called? I forgot. We have this action.
Miyashita-Ulbrich, I think.
Miyashita-Ulbrich action pops out. You have lots and lots of things which are completely trivial classically, and they pop out here, and they make everything work. And in full generality, you don't need anything. You don't need local triviality. All that you need is spatial flatness. Time and again, all the time, you use spatial flatness or a strong connection, if you wish. It's equivalent. Yeah. So without it, you cannot do anything over there. At every single, you have to have spatial flatness. Otherwise, this theory doesn't work.
Yes, but what you are going ahead, because I'm going to say all of this, not with the historical perspective, but I'm going to. Okay. So we have a principal H commodule algebra. So B is echo H, and we have an off ideal, so that we have a principal F H0 commodule algebra. Okay, for this is also for this other H0. Then we have that is a reduction if the two coinvariants are the same, and then if we have a surjective H commodule algebra morphism where we send B to B0, okay, carrying the induced H0 coaction. Let me make a small comment on this algebra under parentheses, because I know that both Gunther and Ayats have this as a hypothesis. In the beginning, we didn't want to put it. It seemed to us too strong. There are actually some very strange examples where you don't have it. But in general, the examples that we were working out does have it. So in the end, we are not so sure it is meaningful. So let's put it in parentheses, because like one, what can I say, one strange example out there may not be important. Certainly, we can see the reduction in this dual picture as before. So the example that we saw before, SL2C going SL2 mod the parabolic, you can see reproduced here, where you take the open U1, right? And you project it in U1 mod N. So in terms of just affine, because we already know that you cannot do it globally with the affine picture, but if we restrict ourselves to the case where A is non-zero, then you can reproduce this definition. And indeed, you have that it is a reduction in this sense. So the algebra, oh boy, I forgot to put the 0 here. I'm sorry, I am very bad. I should put A0 here. So A0 is a reduction of A. Okay, so that is, yes. So, yes?
No, fine.
Perfect. Okay, great. And then we are ready for the Schiff reduction, because we have F and F0 quantum principal bundle. We have we reproduce the same definition. We are asking that locally, this is a reduction. There is no, what can I say, mystery about this. So we have two sheaves that are quantum principal bundle on the same quantum ring, the space, for two different top algebra. One is H, the other is H0, which is H modulo the idea, then the ideal J. We say it is a reduction if we have an open cover that it must be the same for the two. So that we have a surjective algebra morphism, because if E0 is inside E, the functions will be, you know, a projection. F must project into this, so that the co-action invariants are preserved. And so I show you here with the red arrow, you know, the one that is non-trivial. So E0 embeds into E, UI0 embed into UI, and then in the sheaf, because FUI are algebras, right? So they will be surjectively, FUI surjectively goes into F0 UI. So this is the picture. Are we happy before I say the theorem? Because that is the...
Nobody objects.
Nobody objects. All right. So we give an example of sheaf reduction, and then I would like to give you a theorem, okay? So we go to the Takhtajan-Sudbury algebra, and you may wonder why not the Manin. The Manin is the problem, and I will explain to you why the Manin is a problem only later. So we look at this multi-parametric deformation that is known in the literature, and we call it Takhtajan-Sudbury, and I already can imagine Piotr saying that no, it's not really Takhtajan-Sudbury. God forgives me if I don't give the right attribution. Essentially, this is a multi-parametric deformation where we fix some of our parameters. So the Qij, we take them all equal to Q, and the Pij, we all take them equal to Q minus 1. So for example, OQ GL2 has 4 generators plus the determinant to the minus 1, which in this algebra is known as central. Okay, so in the Manin bialgebra, the quantum determinant is central. Not central. However, it has very nice OR condition, as you can see. So because you can flip it with respect, so the multiplicative set generated by the determinant satisfies the OR condition. So we can happily invert it. And so we can look at OQ GLN. Okay, so perhaps not everybody is familiar with this quantum algebra, but it is well known. I think Landi, Dubois, Violette work on this, so it is known. So we take this, and then we construct, we prove that it is a quantum principal bundle. So it is the same construction that we did on SL2, exactly the same. And then you can see directly that the F that is defined as, so you see you define a sheaf of OO on GL2 by inverting A minus 1. Similarly, you invert C minus 1. This will give you 2 open sets, and you define the sheaf here. You have to define it also in the intersection, where you invert both. You see it right here. So you have your F. Then you go to F0, where you essentially are quotienting by B, okay? So the B kills, so you kill that, is the nilpotent, essentially. And so I don't write OQ GL2, because if you kill B, it becomes a very simple algebra. You have A minus 1 and B plus minus 1. Then you can invert C and you get a similar algebra. And then F0. And you can immediately see that that is a projection, very trivially, right? You just project by B. And one F is a sheaf of H comodulo algebra, F0 is a sheaf of H0 comodulo algebra, so that they both quantum principal bundles, and F0 is a reduction of F. So this is an immediate, very simple example. What is non-simple in this example is checking all the co-module properties, but you believe that this has. Now, I present you the result about the principal bundle GLNC going to Pn-1, the projective space. Now, you can prove exactly in this very same way as we see for GL2 that this is F is a quantum principal bundle. And before we look at the reduction, I just want to tell you that here the real difficulty in this proof is to change coordinates because you want compatibility. And then your life is not so simple that you just have to check one. You have to check all compatibilities, and the calculations become a little involved, but we are not scared. So you can prove this is a quantum principal bundle. And then we have the result that if you reduce it by taking H0, where you take not the torus, but the Levy component of the maximal parabolic, you get an H0 quantum principal bundle. So essentially, our theorem tells us that you get an example, a family of example, GLNC modulo Pn-1. This is interesting, but we had really a big question. We were wondering why the Manning doesn't work. Is there some condition that one needs to check that tells us when you can or cannot do? So Piotr was anticipating this because you know this theory, but in fact, it is exactly as you say. There is a characterization of reductions in the affine case that you can extend to the shift theoretic case that will tell you when you can or cannot perform a reduction. But are we happy with this so far, this example, this definition that I can go to the more existence of reduction, so this more involved theorem? Happiness?
Yeah.
Okay, great. So let me go to what Piotr was anticipating from the very beginning of the talk, okay? So essentially, this is what you were saying, right, Piotr? This is exactly what you were saying or not?
Yeah, I mean, that's just very well-known fact in topology.
Of course. Yes. I'm not saying we invented it, God forbids. In the ordinary setting, in the classical setting, you can do a reduction if you can produce a P equivariant map. I mean, the proposition is a bit more involved, but we don't care. What we care is that you have to produce the P equivariant map. And this is actually, as Piotr was correctly saying, it is, I'm coming, Thomas, is bringing the work of Gunther and Schneider into the play, because you may wonder, how do you extend this to the quantum setting, to the non-commutative setting, right? Because it is not as trivial as it looks and brings many complications, and perhaps is the beauty of it. So Thomas, what is the question?
So my question is about this quotient. So
yes,
it's like E set minus K.
No, it's not minus, it's the action on the right. So it's the quotient on the right, it's not minus.
Yeah, so this is should be slash, not backslash.
So I think it's the fault of Chiara. So I'm happy to give the fault to somebody else. I, Thomas, would write like you with a slash. But Chiara insisted that since the action is on the right, the slash should be in the other direction. But okay, we understand each other. It's a quotient, indeed. It's not a set minus. Absolutely not. Okay, thank you.
Because indeed this looks like you are dividing K on the left by P.
No, you are right. You are right. This is an unfortunate annotation. So is he going to P mod K? That's what it is, the quotient. Yes. So.
Yeah, but that's just, of course, a triviality is a notation, nothing else.
Yes,
but
sadly, the notation can never make everybody happy. And I put here a little example just to convince ourselves that indeed it works nicely. And in fact, in the example, you see immediately that it is the quotient. And you can produce, you know, this reduction by giving a section, global section, from the SL2C to P mod K. And you build it by doing local and patching. I put it here because that's a strategy for quantum. Now, finally, the existence theorem for affine quantum reductions. And this theorem is due to Gunther and was again rewritten and rearranged in a more conceptual way in the work by Ayats. So this existence theorem says that you expect, and I put it right here.
It's not correct. I mean, this is definitely not Ginter's theorem. I mean, first, no. I mean, first, as I told you, neither Ginter nor Scharrenburg had the correspondence at the level of ideals on one hand side, or reductions if you want, and maps on the other. That's the last step which we did. And also Ginter was, I think, limited to pointed coalgebra. So this is a very wrong attribution.
Okay, I am so sorry about it. So you should do that.
Yes.
I am sorry. I put it before. On this point, I was, what can I say? I was misled because reading your paper, you attributed it to Gunther. So I was, but you were more about this. So
I attributed it as, not this theorem, but look, this theorem has like 8 complicated steps. And 8 steps were done by Ginter.
Okay. Okay.
That's why it's just wrong not to give him credit, because 7 out of 8 of the theorem were done by him.
I apologize. Should be.
Yeah, interested. You see, Ginter was I mean, he was an algebraist. I mean, he was interested in pure algebra.
No, it's true. Yes.
That's why we wanted to have it at this level, because for us it's not algebra. For us it's like quantum reductions, you know.
Okay, so let us. I fully understand. In fact, I was saying Ayats before because I know that Gunther did not put it fully in the context of principal commodule algebras.
I did it for equivalence classes. Okay.
Yes. So let us look at E going to P mod K. One see classically that this is totally equivalent to going to the coaction invariance by H0 of H into the algebra of function of E. This is obvious. This is really like a very simple fact from algebraic geometry. However, when you're looking at the Hopf-Galois reduction theorem, Gunther Ayats, you see that the reductions, where B are this coinvariance for A, you see that the reductions are not captured by the maps from the coaction invariance co H0H into A, but you need to take the centralizer of B into A. So this is kind of a surprise, right? You have to look at these maps, and this condition must be put because you need a two-sided ideal, but also in the proof plays a key role. In particular, there is a Jeter-Drinfeld module structure on the ZBA and the Miyashita-Ulbrich condition, on which I will comment if I have time, okay? But this is just, you know, I am sorry, I get disturbed even when I give a talk. All right. So far, so good. So this is just a theorem. Now,
the theorem holds for the reduction being the map being an algebra map.
Yes, indeed. Yes.
Thank you.
Okay, thank you. All right, so let us see what we have done for the Schiff theoretic point of view. So we take a quantum principal bundle over a quantum ring, the space for a finite open covering, okay? So for now we look at this. And then we look at H0 as H modulo some Hopf ideal. And then we assume to have a family Fi, H commodule and H commodule algebra maps, so that we have a certain commutative diagram. Why do we need this? It is necessary because since we want to make a claim about a reduction, a sheaf reduction, we need a sheaf. So we are not content of getting a family of maps. These maps should be consistent with the sheaf theoretic setting. So they should patch. And the row, indeed, are the restriction maps from the UI to the intersection. Hello? From UI intersection.
But I'm not. I don't have.
Hello?
So, Rita, but you see, yeah, Ludwig logged in on his smartphone into Zoom, and then we had a sound loop, okay? Yeah, I know how to do it on smartphone without having a commotion, but Ludwig doesn't. So.
Okay, so can I go ahead?
Yes.
Okay, perfect. So we're saying that in this theorem, we need to ask compatibility of the family of Fi with respect to the restriction of the sheaf F. So the row will restrict FUI to FUI intersect UJ, okay? And so this diagram must commute. Once you have it, then F admits an algebraic reduction, F0 to the group H0. Now, how do you build technically? So you have to take a quotient sheaf F mod I, okay, which goes into the process of the sheafification, because if you take a quotient of sheaves, not necessarily a sheaf, and the ideal sheaf that you are considering is simply, you apply to rho, so you have FUI, which is your algebra, applied to this very strange object, which I'm sorry, the slide is gone, but this mimics the ideal that was in the previous. So let me quickly show you. So you see, this was the ideal, right? A, F, and then this object here, and A is played by FUI, and that's the object. And then you need the restriction. Now, what we are doing, we're giving this ideal sheaf for all the UIs where big I tells you the intersections. The reason being that the intersections of all open coverings in a final open covering is a base for the topology. So if you reach a base of the topology, you really have no problems in defining the sheaf. Okay, so this is the reason where we had to go to this particular open sets. So guys, are we happy with this very strange theorem?
No objection from me.
Objection. Now, this is a very interesting theorem, which is the sheaf theoretic analog of the Gunther-Ayat's theorem, prescribing when you can have a reduction. And in fact, what we prove is that for the algebra of the Taitajian-Sudbury, there is such condition, but the Manning deformation does not satisfy the hypothesis of the theorem. Where is this hypothesis failing? Because let me go back and then I will comment this. You see, you are asking that this Fi goes inside the center, the centralizer, sorry. But this is very strong. This condition, you don't see it in the commutative case. But in the non-commutative case, going into the centralizer of something, this is an incredibly strong condition. So for the Taitajian-Sudbury algebra, where it is only mildly non-commutative because it doesn't have the long relations, you have some hopes. But the Manning, unfortunately, this is a very non-commutative algebra, right? So, and then you essentially have no hopes to get into the centralizer of some element that is generic somehow. And so essentially you have no hopes that this theorem is verified. So we prove that for the Taitajian, well, we checked that for this algebra, indeed, the condition is satisfied, and we are glad to say that it is satisfied, because we would have a problem because we proved it before without this. And we are able to define the family of, so this is the family FL of the previous theorem explicitly, really explicitly. And we also think we have an idea on how to do it beyond the case of the projective space, which is somehow a very, what can I say? It is a very minor case. So our hope is to do it for the Cartan, sorry, the parabolic geometries. That is really what we are after. And if you, and I even have an idea on how to do it. Is a bit involved, but couldn't do it by the time. So we reproduce an example of this theorem. And finally, oh, sorry, let me go back. So Thomas, what is the question here? Because I wanted to comment the bibliography.
Okay, so my question is about, could you come back to your compatibility condition?
Yes.
Yes.
Yeah.
Your
Yes,
theorem.
yes.
Yeah. So this is the condition for what?
Okay. So
Because maybe I will explain myself. So it looks for me like a condition for the sheaf of ideals. Okay, so which means that it's a condition for admissible reductions.
I'm not sure I understand the question.
Okay, so
In order for the sheaf of idea to be well defined, you need this condition. Is it the answer?
yes,
Yes.
yeah.
Yes, in order to define the reduction, in order for this ideal sheaf to be well defined, you need this condition. Yes.
Yeah. So this is the condition for the condition limiting possible restrictions, possible reductions.
Reduction, yes, yes. Because in order to construct the quotient sheaf for the surjectivity, you need ideal, of course, right? You need ideal sheaf. And in order the ideal sheaf to be well defined and locally to satisfy the Gunther-Hayat theorem, you need this commutative diagram. So it is okay, you are telling me it is not a smart theorem. Perhaps you are right.
No. I'm suggesting something different.
Yes.
Because I have this Manning example in mind.
Yes.
When it simply means that in this Manning case, the only reduction would be possible if this ideal would be zero.
Okay, so locally we can produce Manning algebra, because if you limit yourself to an open set, you can do it. But if you want to be global, then you cannot reduce, because, well, okay, I was wrong. We were trying to reduce the example SL2 to the projective, okay? We were thinking about that. And that one we proved that is not in the center. It's centralized.
Yeah.
So that cannot go. Okay. So we
so this was simply a wrong reduction. So the only reduction in the Manning case is identity. Probably.
I don't know, because okay, so certainly the one going from SL2 to the projective, it cannot go. But perhaps there is something else which I cannot imagine that would go. I don't know. You see what I'm trying to say? I would, but right, I don't see how it could go another reduction.
Okay.
I can tell you about Manning reduction if you want, but I need a little bit of space. Can you go to a slide which is less dense?
Perhaps.
Yeah, that's fine. Okay, so because you guys were discussing it so fiercely, we give an example which I have with, will be produced with Rainer Mattes, but then we studied reductions with Bartek Zieliński, and I think it's a very entertaining example. So The story begins like this. I mean, I'm sure you guys know Ves-Zumino calculus, right? There is some kind of Ves-Zumino calculus on the mining quantum plane. That's sort of like various times. And so we were thinking the following. Of course, plane is trivial, so all associated bundles like cotangent bundles are also trivial, all right? So they have to be free modules, fine. But you see, when you have something associated with Hopf-Galois theory, it's not just a module, it's a bimodule. And the Ves-Zumino calculus has a very interesting and non-trivial bimodule structure. So what we did was the following. We took this, let me denote it by M.
Piotr, I don't see anything written. Oh, you're writing now. Sorry, now I see it. Okay.
So let M stand for this mining plane algebra, okay? And then we took a smash product. Yeah, I mean, we want this bundle to be trivial, right? The frame bundle of the plane is trivial. So we're looking for a smash product with a GL Q2 algebra, how it would be classically. So I'm writing with a mouse, so it's a little bit difficult. And it's all just purely algebraic, okay? So we're thinking, so that's a Hopf-Galois extension, it's a smash product. Now I take this associated bimodule, and I want this associated bimodule with an appropriate representation. I want it to be precisely the Ves-Zumino calculus, okay? So this way we determined this smash product. It's a beautiful smash product. It has very nice structure, and it reproduces the Ves-Zumino calculus as a cotangent bundle, as an associated cotangent bundle. Okay, so now we ask ourselves the following question: Can I reduce this smash product to SLQ2? So in other words, I'm asking whether the quantum plane is orientable. Okay.
Okay.
Can I reduce it to SLQ2? All right, and precisely because of this condition, because of this centrality which you are talking about, we proved that the reduction exists if and only if Q is a cubic root of unity.
Of course, yes.
Yeah.
The similar conditions too. If you wanted, so Q becomes severely restricted, yes.
Yeah, and that's because only then you are central. Only then the condition simply you have to have your map has to be equivalent with respect to the Miyashita action, and you have it when this Q cubed is equal to 0.
Yes, I prepared the Miyashita-Ulbrich action as an extra slide because perhaps you wanted me to show. It's a very hard action, but it is important and like necessary because you are looking at the right H-module, H-comodule algebra structure of this object. So you really need this action. Otherwise, it makes no sense, right? If you don't have it. Yeah. So this was an extra. Okay. Thank you very much for the attention. Thank you.
Thank you so much. Okay, so now time for questions. Tomek, do you want to ask a question?
I am curious who's here. Very curious. Oh, my collaborators are here, so I'm glad.
So you said they listen to your talk. What a waste of time. They should be working.
Right.
Tomek, go ahead.
Okay, so I'm not sure exactly what is happening in this Manin's case. Because of Piotr's comment,
yes.
Are you sure that this reduction is impossible for all Qs, or for maybe it's possible for some Qs?
Yes, for some Qs, yes. I think, Chiara, can you remind me? I think we found for Q1 minus 1, I forget. So there was some condition on the Q. Am I right? Chiara,
sorry, I couldn't find the microphone. As far as I remember, we had a problem with all Q. we couldn't find, at least in trying to reproduce exactly what we did for this algebra, we could not define the A0, the sheaf F0 on one of the two charts for a specific algebraic reason. I mean, the generator you would kill. The ideal containing this generator contains also the unity, so it's not a good. We couldn't do it in the same way, but we are not sure that this is the only way in which you can get this reduction. Maybe you can do it in some other ways, but we don't know. But already at the level of SLQ2, so the easiest example, the lowest dimension.
You see, Thomas, you're asking a difficult question because you're saying, are you sure you cannot do it? So the answer is, we could not do it. Then we discovered this theorem and we checked that we were not getting into the center. And so we thought, okay, great. It means that it cannot be done. But truth is that perhaps there is some other idea that allows me to get into the center in some way which I'm not able to think of. So it is difficult to show you can. You see my point, right?
Yeah, but my question was much simpler.
Okay.
In the spirit of Piotr's comment.
Yes.
Is it possible? Would be it possible to find such a reduction for some specific Qs, parameters?
Okay,
Yes.
it seems to me, but now Chiara is not agreeing with me, so I don't remember, that at some point we had to say that AD was equal to DA, which means the Q square must be 1, right?
Oh,
We arrived to that. I think, Chiara, we did arrive to that, didn't we?
That it's possible, but it was something so easy as Q square equal to 1.
Yes, so if Q is equal to 1 or minus 1.
Yes.
But we thought that was not reasonable, so we didn't pursue that road.
Okay, thank you. Now I understand.
Excellent. Anybody else? Zoran, you were visible for a while. Do you want to ask a question?
No, thanks.
Okay. Adam, you are so quiet. Where are you?
No, I don't have any questions. Thanks.
Okay. You decline to comment. Okay. You plead the Fifth Amendment. All right.
Piotr, you asked so many questions that I hope I clarified everything during the talk. So it was.
I am very happy. So if there are no further questions.
I have a comment.
Oh, go ahead. Ludwig.
I didn't know about this reduction from Piotr, I don't know why, but SLQ3 is at roots of 1 is very important actually. Kohn suggested it's maybe important for symmetries of the standard model and also it's non-trivial covering of quantum Lorentz group. So
okay. Then perhaps what we discovered was non-trivial. I don't know. Okay, I don't know.
Thank you, Ludwig. Andrei, you want to ask a question? No.
No, thanks. No questions.
All right.
Okay, so it seems we are done. I absolutely loved your talk. I'm biased because it's my cup of tea, but it was extremely enjoyable. And I love the way you explain and speak. For me, it was a joyride all the way. So let's thank.
But Piotr, I thank you. I thank you. Sorry, I cannot really clap, but I thank you for this opportunity. And I really want to get a hold of you and your group because we have to talk about many things.
Yeah. And remember, you promised to show me the Ferrari museum. So
That's true. That's true. You have to come to Bologna. All right. Very good.
So let me stop recording. Okay.